Well, welcome back, gang. Welcome to part 2 of this unit on yield monitors. In the first unit, we kind of went into the basics of what a yield monitoring system is, what its goal is, and then looking at some of those basic components that we need to have. In this part here, in this second series, we're going to look at some more of those components that are required, what we need, as well as the calibration part of it, and trying to determine what our yields are going to be through the system. So we'll go ahead and get started. So one of those other vital components that we need to have in that combine is we have to figure out what our speed is. And so that's going to determine our area, or our acres or hectares, along with the width of the header. And the header width is a setting that we're going to put in the system. So we still need to measure the distance that we travel. So speed is measured by three methods of what we typically see on a harvester: a shaft speed sensor, a radar/ultrasonic sensor, and then our good old GPS receiver. So to begin with, a shaft speed sensor, this is my rudimentary drawing of it. What we see is down on the drive unit of a combine. Coming out of the drive unit is a shaft that heads over to those front tires, and that's what makes the whole combine move. Well, on that shaft that comes out of that drive unit over towards the tires, on that shaft we're going to mount a magnet. And across from that magnet, somewhere near the frame of the combine, we're going to mount a sensor. And what happens is when that shaft spins and that magnet spins, as I put it into animation here, as that shaft spins around and it takes that magnet around, as soon as the magnet comes around and comes back near that sensor picks up the signal of magnet and counts it. So what we're recording here is recording how many times that magnet will go past the sensor in a given amount of time period. And so it calculates the speed from that. So that's what a shaft speed sensor is. The problem with it is it's not 100% accurate. The reason being is if you look at a lot of agricultural equipment these days, is all the power that we put in the tires to drive forward, it's not 100% efficient. We have this thing called wheel slippage. In fact, a lot of tractors today, if you look on the tractor, in the cab, there's usually a gauge or something that's telling us how much wheel slippage we have. So it's not 100%. So the shaft sensor, speed sensor, may think that we've moved 10 feet when reality is maybe we only moved 8 feet because there was an additional 2 feet of tire spinning going on in that time period. So that's one reason. Another reason is as when you think about a combine, we have combines now that can have a 300 bushel grain tank on them. Well, when that combine is sitting empty versus 300 bushels of grain in it, you're talking a big difference in weight. So as we add more grain into that grain tank, that's going to give us a heavier load, which is going to put more pressure on the tire. That tire is going to have a tendency to squat a little bit, so it's going to kind of reduce that rolling radius. So once again, it's not going to be 100% making a complete round revolution. So it's going to give us an inaccurate speed reading because of that. So in terms of yield monitoring, a lot of older systems, this is what they utilize, and you could tap into it if you wanted to, but you're not going to get a really good speed setting with it. Another thing that we've seen and we're able to use is to use a radar unit or an ultrasonic gun. These things are more accurate than a shaft sensor. It's like a radar unit that a typical law enforcement or police or sheriff may have. So basically, it's a gun that's going to send out radio waves at a certain frequency, and it measures how much time and the frequency of that signal coming back, and it equates it into giving us a speed reading. So the problem with a radar unit is that if we're in some really rough surfaces, and if you look at a cornfield right after the combine's gone through and picked it up with the head, there's a very rough surface there, depends on where that radar gun is at. So those rough surfaces could alter the frequency and the timing of the signal coming out of the gun and coming back into it. And the other thing too is that you need certain clearances, typically about 2 feet out in front of it, and at least 2 feet above the ground is where you have to have the radar unit located. The reason for that is here's an example here. So I have my green piece of equipment, and the yellow part there is my radar gun. The radar guns are typically aimed at about a 45-degree angle down at the ground. So as soon as we start moving, as I put into animation here, it's basically recording, the amount of radio waves that are coming out of the gun and how fast it took for them to come out and bounce back and pick it up. Now, if I don't have the right amount of clearances, like if something in front of it is blocking it, well, then the radio waves, the waves and the frequencies being generated from that radar gun are going to hit that obstruction and bounce back a lot differently and give me a different speed reading. We had this in our combine. Our first yield monitor that I had in our combine used a radar gun. And we had the radar gun mounted off the front drive unit basically underneath the feeder house. We noticed when we got into soybeans that our radar, our speed reading was way off, and there was a lot of fluctuations. It wasn't until we got underneath there and measured it that we didn't have enough clearance in front of it, so it was picking up scattered signals from the back of the feeder house, because that feeder house ran a lot lower in soybeans than it does in corn. So once again, these are good. It's a lot better than having nothing, but it does have an effect if you don't have it mounted correctly. Our third type, this is our best method for determining speed, is using a good GPS receiver. And the best part about it too is, well, since I have that GPS and I'm using it for speed, I'm also going to be able to record my yield location, my yield information at that location. So it's going to go along and say, yep, here was your coordinates. Combine's going to say, at these coordinates, this is what I was picking off from the moisture sensor, this is what I was picking up from the grain flow sensor, and let's go ahead and start making the yield map. So this is the best method we have, and there's additional benefits from utilizing this. The biggest issue we have to worry about with a GPS receiver for determining our speed is the accuracy of the receiver. If you go back to our unit 2, when we got into the basic GPS systems that are out there, those that didn't have that differential signal, we had the capabilities of having those things off by 2 to 3 meters, 6 to 9 feet. If you think about it, if you have a GPS that is not that accurate, 6 to 9 feet accuracy, that equates to, you can run the calculations, that gives us a difference of about 5 to 6 mile an hour. So that's a pretty big variation if we're using a very low end GPS signal that does not have any differential, any correction into it. The other thing you think about is, the faster you go, the more variance we can see in speed, especially with some of those older receivers, or those that don't process as fast. So once again, we can see some, my location may be at this location, but the GPS may think that I'm 5 or 6 feet away, or even further out in some cases. And so that's not going to give us a really accurate yield map when you look at it. So one of the other things we want to look at with that GPS is what we call that Hertz rating. Remember back from that unit, is the Hertz is how many satellite signals can it process in a given second. So the more Hertz we have, the more signals we're processing in a given second, so a little bit better positioning. So a 10 Hertz receiver is going to be better than a 5 Hertz, which is going to be better than the 1 Hertz receivers. Something to think about. Okay, our last kind of vital piece of equipment that we got to have, or component we got to have, is what's called a header position sensor. And basically this is a sensor that's going to tell us when the head is up and when is the head down, and when do we need to start recording data and information. So it is automatic. And so what we want to do is be able to say that when we raise the head up, so we get to the end of the field, we pick up the head to turn around and drop it back in to pick up our next set of rows. When that head raises up, I want the system to stop recording. I don't want to be collecting any data. Vice versa, when I turn around and I drop that head back down, I want it to be able to start collecting data. Now, if we didn't have this header position switch sensor, then it would be up to the operator to basically hit the button on the screen, or to say start recording, stop recording, start recording, stop recording. I've done that in a few other operations, not with harvesting, but a few others. But a lot of times you forget to hit that button to turn it on or to turn it off. So we need something automatic, and that's why we have this. Most typical systems, a lot of the older combine systems out there, typically what you have is a spring-mounted arm that kind of sits up underneath the cab, and to that is there's a spring with a chain attached down to the feeder house. So as you drop the feeder house, that's going to drop, but the sensor is going to stay fixed to the cab. So when we stretch that chain out, pull on the spring, it's going to activate the sensor and say start recording. So newer models, they have that built into the factory. So in newer systems, all you have to do is you just tee into or tap into that cable into that sensor and feed that into your display system. So the other thing that we see a lot now these days is that we've also kind of combined it with there's an elevator speed sensor. A lot of combines on that clean grain elevator, there's a speed sensor there. That just lets us know that it's running, and if it quits, then we know something's going on. But we've also tapped into that, so that way we know when the combine is actually running and we can record. So a scenario here would be prior to that in an older combine when we had yield monitoring, we didn't have that elevator speed sensor and we weren't tapped into that. So my dad would be combining, he'd lift the head up, it would stop recording. But at the end of the day, he'd come up into the yard and he'd go to park the combine, and of course he always puts the head down because he doesn't put any pressure on the hydraulics in the hydraulics underneath the head. So he would always drop it down, but if he still had the system turned on, well, it would start recording, and it would think, hey, you put the head down, you want me to record. Even though the combine's not running, so it's recording 0 yield. And so at the end of the year, when I download the data, I always have to go back in there and delete those out or fix those. Now that since we've also tapped into the elevator speed sensor, so most systems right now, they're not going to record until that elevator speed sensor is actually producing a certain speed, typically 350 RPMs or higher. It's not gonna record unless it hits that mark. So it kind of helps out with that. So that way, at the end of the day, if you go to drop the head, but the rest of the combine isn't running, it's not going to record. So here's a couple photos of some header position sensors. Once again, like I said, a spring-loaded chain there on the left. You can also see it there on the right-hand side, what's kind of circled in yellow there. So that's the function of the header position switch. The last thing we got to have is, well, we need something in the cab to know what's going on. So we have to have that good old display console, what we talked about in the last unit. So obviously that display is going to be mounted in the cab. That's a kind of a no-brainer. And yeah, as we kind of learned in the last lesson, this is where all of the data is coming into it. It's collecting and gathering all that data, calculating it, what's being fed in from all the sensors, what's being fed in from the modules. And it's also allowing us to see what's going on, change some of the settings in there, set things up, do our calibrations and all that sort of information. So kind of a vital piece that we got to have. So that's in terms of basic components. So we'll kind of switch over to the other side, to the calibration. So there is several calibrations that need to be done, and the reason for that is if you remember back to that grain flow sensor, we have grain hitting that impact plate, and so we have to take that signal and turn it into bushels. So we have to hit that mass, and we have to have a way of so that the system knows whatever amount hits it, it can equate it to bushels. So there's a lot of calibrations that need to be done. One of the key ones that we're going to look at is, and think about this, is that combines have lots of moving parts. You think about it, when you fire up that combine and you go and engage it, we have to run, the threshing unit underneath. There may be some of the separation stuff further back, the fans, the elevator to get up to the clean grain tank. We also, if we're running the unload auger, then we go to start up the head. So there's lots of moving parts, and all those parts move in different harmonies. And when you start combining different harmonies, that's what equates to vibration. And those vibrations, if that vibrations are going on, those vibrations are going to be picked up by that force plate on that grain flow sensor. So that plate is going to interpret those vibrations of, oh, something's hitting me and I need to record that yield. So that plate is going to record what it thinks is yield, when the reality is I still don't have anything going through the combine. I'm just running the combine. I'm not even harvesting grain. So we have to factor those vibrations of the combine out. We basically have to nullify them. So what we do is what's called a vibration calibration. And so at the beginning of every crop, when we go to start combining, say, soybeans, we're going to do a vibration calibration, and we're going to do this every year. And for every crop, we're going to basically power up the combine, run it full bore as if we're combining, but we're just not going to combine. And then we go into here and we do what's called a vibration calibration, and it's basically recording and canceling out those vibrations so that when we do get in the field, it's going to take those vibrations, not utilize them, and so what's actually hitting what the plate is going to record is what's actually hitting it. Alright, next couple calibrations we need to take a look at that are fairly important. One of those is the shaft speed sensor, and that is only if it's going to be used, if we don't have the GPS or don't have a radar unit. The shaft speed sensor, they don't know what their distance or what their speed is, so typically we have to calibrate that. So that way those sensors will know what that distance is, and then from that it can compute that into speed. Typically the way they work is you measure off a known distance, and what I have seen has been 700 feet. I've seen an 800 foot. I've also seen 1,000 foot. What you do is you measure off a known distance like that, 1,000 feet, take your combine to the starting flag, and then you drive that distance. And when you get done, you hit stop, and then the system will say, if that was 1,000 feet, I recorded 890. So then it does the calculation and calibrates it accordingly. So then it can calculate the speed a lot better. So travel time is another one. And by travel time, it's not traveling down the road or anything like that. What we're looking at here is how long does it take for that grain to go from the front of the combine when it comes into the head of the combine till it hits that grain flow sensor. It's not right away. It takes some time to do that. So we have to be able to log that time, record that time, and every combine, every crop will be different. And we time that so if we're using a GPS, it'll know what that yield was when it was coming into the head, not when it was hitting the grain flow sensor. Some combines, it could be anywhere from 10 to 20 seconds sometimes, usually in that range. And you think about it, in 10 seconds or 20 seconds, there's quite a bit of distance you can cover. So we need to be able to dictate that time. It's the setting. It's not really calibration, it's more of a setting. And so here's a prime example of showing you what happens when you don't have that timing set correctly. So this actually came from Ag Leader a few years ago. They kind of did some research on this. And as you can see at both ends of the field here, we have some red strips. And that was because the combine wasn't, the timing wasn't calibrated. So it was either set to, or it was set way too early. So it was saying start recording after 5 seconds when it was probably more like 10 to 15 or 20. So this was from 1 year. They came back the second year with the same combine, but it put in a more accurate setting of a time delay. And as you can see here, this is what they had the next year. And you could see a big difference on the ends. So timing is huge. If you look back at here, all that red will actually add up. As you start looking at data, it does factor that it does factor that in, and it does alter the information that we're looking at. So something to think about. Not a lot of people put some thought into that. That's something that typically gets overlooked a lot. Some other calibrations that we have is there is a temperature calibration. The temperature calibration helps us give us a better, more accurate moisture reading. As I said, moisture will affect the mass of the grain. Likewise, temperature will have an effect as to what happens to that moisture that's in that grain. So we want to take an accurate temperature reading. In a lot of displays, you get into the temperature thing, and you could set it. There's like a thermometer on the system, and so best thing to do, take the combine, go park it in the shade for at least an hour. Let it kind of get acclimated there. take a temperature reading in that shade, and then put that into the system. And once again, it's going to offset it. It's going to calibrate it accordingly. Or the other suggestion is do it first thing in the morning before the sun gets up and hits the equipment or hits that sensor. So do it first thing in the morning, or park it in the shade for at least an hour. Another calibration is looking at that header height. We talked about the header height sensor. There's a few things we need to calibrate it. As I mentioned earlier, different heads will run at different heights, so we have to calculate it for different crops, different heads. And sometimes we may have to change it for field conditions as well. In these, typically we have 3 settings. When we go to calibrate it, we have to calibrate, what's the highest that head will go up. So it will tell you raise it all the way to the top. You hit a button and it says, okay, that is what's considered the highest. Then you're going to take that head and you're going to set it down as low as it will go, and you can record that. That's going to be the lowest setting when it's down on the ground. And then the third one, this is kind of the more critical one of the 3, is what's called the record stop height. And what you're going to do is you're going to pick that head up to a point where you say, okay, once that head gets to this height, that's when I want you to stop recording. So you just lift the head up to where you think, this is where I think it will be, so I may want to set it there. This kind of comes back into those field conditions. We have a field that actually has quite a few waterways through it, where we have to pick the head up as we go through it. A couple little small, washout ravine type things. Typically in there, I have to set that record stop height a little bit higher, because sometimes I got to pick the head up a lot higher, even though I don't want to stop recording. So those are things that kind of have some effect on some of the calibration settings we look at. Okay, one of the biggest calibrations, and this is the biggest one because this is what determines our yields, and this is what's called load calibration. And what we need to do is we have to record, take a measurement of grain and say, okay, this is how much this grain weighed, so that way that grain flow sensor will know this is how much came through, and we start calculating those bushels. So a couple things to know about load calibration. You need to do it at least once per year per crop. And each time you do that, you need to do about 4 to 6 loads. And each one of those loads has to be anywhere from 3,000 to 6,000 pounds. So as you're going through the field, and you're ready to do a calibration, this is when you're going to have a weigh wagon nearby, or if you have scales on a grain cart. So go out and you combine maybe 3,000 pounds, 6,000, anywhere from 3,000 to 6,000 pounds. Do that 4 to 6 times. Now, each load, when you go to do one of those loads, each load should be something unique and different. And that each load should be from a different area or a different quantity. So maybe one load's going to be at 3,000 pounds, the next one's at maybe a little bit more, 3,500, then a 4,000, 4,500. Make them of a different area. And maybe the first time it's, a quarter acre, then it's a half acre or a third acre or an acre, 2 acres, whatever it may be. You also want to do it at different speeds. So maybe one load you're going to do it at 3 miles an hour, the next one is at 3.5, and maybe one at 2. But you want to do it from a similar variety. So don't start in one variety of corn that has a really great stand, and then your last loads are going to be in a different variety where maybe it wasn't standing so well. So you want to use where it's pretty much the same variety, a more uniform type crop. So when you look out the field, and you look for some uniformity out there, that's the area you probably want to focus in on when you combine it. And the other thing too is no high flow loads. High flow loads in a very poor yielding area. This is something that came through Ag Leader a few years ago, where it is you have a poor yielding area, but then all of a sudden there's a lot of it coming through, a lot of materials. So you want to try avoid that. So what you do when you take a load out, you combine a load anywhere from that 3,000 to 6,000 pounds out of a different area at a different speed. You're going to weigh that load out. Use a weigh wagon. Your local ag service provider or your local seed dealer should have one available. A lot of grain carts have them on. There's been some questions lately about, the accuracy, some of those scales, being certified, trying to get a more accurate weight. As long as it's fairly close, you should be good enough. So what you're going to do is you're going to weight out each one of those loads. Then you're going to go into the system and the display system, and you'll enter in, here's what the correct weight is. So the system is, you say it's a calibration load, and it's going to say, hey, I think I just combined 4,200 pounds. You go in and you combined it, put it in a weigh wagon, you came back and said it was 4,400 pounds. So you go in and enter 4,400 pounds, and it's going to do the math and the calculations and factor, and adjust accordingly. The other thing you want to do at this time is you want to measure your moisture. So you take several samples coming out of the grain tank, measure those moisture readings, and don't just take one. Take 3 or 4 and average it. Make sure that your moisture tester is also calibrated. The ones that you get from a local Fleet Farm store, they're good to begin with, but you have to keep them calibrated. So make sure it's calibrated, and you can do that with your local ag service provider. And once you do all that, the system's going to go in and do its calculations, create the offsets, and everything should be good. So, a couple of things to note with load calibration. You don't have to do it at the start of a crop or at the start of a season. A lot of the systems these days, it can be done anytime. If you did it mid-season in corn, you do a calibration, it's going to go back and make adjustments to all the data that was previously gathered for that crop year. And you can do it numerous times. You just don't have to do it one time and forget about it. Prime example for me is we have a grain cart, and our grain cart has scales on it. So typically about once a week while we're out combining, we'll just take a few loads here and there, and we'll just do some calibration runs on it. Take the weight off the grain cart, put it in there. We keep doing it. The example we had a couple years ago, we did that. We constantly did calibration loads throughout the whole season. We got done, everything was in the bin, some of it went to town. It was unfortunately one of those years where we thought we had a potential insurance claim because of some preventive planting acres. So when the insurance agent came out, he took all the measurements of the bins, what was in the bin, took a look at all the scale tickets of what we had taken to town. He did the calculation, came up with, here's how many bushels he had for corn. My dad mentioned I had a precision ag system, so he took a look at our precision ag data, and he came back with afterwards and says, your system was off by 0.05%. So we were less than 1% off. And he said that was probably the best he had ever seen in a long time. So and it goes back to we constantly calibrating through the season as we're going through that crop. We keep dialing that system in more and more. I forgot to mention this on the previous slide when I said, we're going to do it at different speeds in different areas. We're trying to put as much variation into the system so it can factor that out and adjust accordingly. So that's why we do that. So yeah, you can do it numerous times throughout the year. The key thing here, and this is kind of why I have it in big, bold letters, and I kind of put it in brown, so it's garbage color. Garbage in, garbage out. You're going to see this come up later on in the semester as we talk about data, but if we don't do a proper load calibration, we're recording garbage. And when we take that information out of the display and we put it into our systems later to analyze it, it's not going to do me any good because it's garbage. It literally is, because if it's not calibrated and it's not taken into account, that information is useless to me later. It's not going to help me find out, it's not going to give me those poor areas or those better areas. It's useless. So you want to make sure you calibrate your loads all the time. So if you're going to invest money into a precision ag system, get the most out of it. So more calibrated data is going to give you more accurate data. Kind of gave you that example earlier. So here's kind of an example from what calibration looks like on ag leader systems. So when you're in there, you just in the bottom left hand corner of the display, you say there's a grain calibration. So whether it's a weight or a moisture, so if you would do it's a weight calibration, you go in there and say, yep, I'm doing a new load. You go and you combine it out. Once you're done, you come back into there, and you can kind of see there on the right hand side what it looks like. says, yep, here's the weight, here is the actual. So you plug in the actual, and then it does its calculations. The nice thing too with this system is you can see check marks over there. You can actually set which loads you want to utilize as part of your calibration. Just it kind of helps you dial it in. So if you had one that was way off, maybe there was something there that you didn't realize, like grain was already in the tank, or grain was already in the grain cart, or on the scales. So you can uncheck that and say, nope, don't use this one. So okay, moving on. So when to calibrate? When should you do it? Or when should some of these certain calibrations take effect? Typically, the start of the season, two big ones is that temperature. Like I said, park it in the sun or park it in the shade for an hour, take a temperature reading, plug that into the system. And the other one is maybe as you're just getting started, see how long it takes for the grain to come through the combine and get up there. A lot of times when I start seeing it coming into the clean grain tank behind the cab, typically I'll subtract about a second off of that, because I've seen it takes it doesn't take very long in our combine to go from the grain flow sensor into the tank. So I kind of adjust it accordingly there. So that's the start of the season. And then for every crop, what you want to do is you want to do that vibration calibration. Obviously you want to do those load calibrations, the moisture calibration, as well as set your header height, changes in your header height sensor. So that concludes it for this second video series. In the next one, we're going to look at where are some areas for potential errors, as well as some of the kind of general maintenance with yield monitors, and then kind of what's coming down in the future. So we'll see you then. Thanks.